So in a circle, or you can have two circles that are congruent. We have two minor arcs. What's a minor arc?
Less than 180.
Good, less than 180 degrees. So let's draw these minor arcs on our paper. You want two of them. And it tells me that these two minor arcs are congruent if and only if their corresponding chords are congruent. What that means is that from here to here, isn't that a chord? And then from here to here, that's a chord. They're saying if those red chords are congruent, then the arcs are also going to be congruent. Which means if those red chords are congruent, they are the same distance from the center of the circle. That's the only way they can be congruent. Okay? They have to be the same distance. Over the last several days, we've been talking about angles that look like this. What kind of angle is that? Well, what did he call? Where's the vertex?
It's on one side of the circle.
It starts with an I. Inscribed. Very good. This is an inscribed angle right here. Okay? Now, we're going to be talking about a whole shape. Notice here that I put this, how many sides does that have? 5. What's that called?
Pentagon.
A pentagon. I put this pentagon on the inside, and all of these vertex are touching the edge of the circle. Notice right here, what kind of angle would this angle right here be? Where's the vertex? It's on the edge of the circle, so this is an inscribed angle. Well, when I put an entire shape in there, what we call is we say that that whole polygon is inscribed in the circle. So in order for it to be an inscribed polygon, all of the vertex must touch the side or the edge of that circle. Is the circle on the inside of the polygon? Is the circle on the inside of the polygon? Where's the circle? Outside. The circle is circumscribed about the polygon. So the polygon is on the inside or inscribed inside the circle. And the circle is on the outside, circumscribed around that polygon.
So the polygon is said to be the same.
Inscribed, INCRIBED. And the circle is circumscribed. CIRCUMSCRIBED. Okay, so let's take a look at the example. We have a trapezoid, ABCD, is inscribed in circle O. Okay, so trapezoid ABCD is inscribed in circle O. Not that it's just on the inside. What's more important is that all of these points are on the edge of that circle. They have to be in order for it to be inscribed. Then they're telling me that, what does this mean? Right here. So let me ask you a question. What is AB called? The chord. So what this is really saying, because in our brain we think line segment, but when we start talking about circles, that's a chord. So it's telling me that chord AB is congruent to chord BC, which is congruent to chord CD. And then it tells me that arc BC is 50. So how big is arc CD? 50. And how big is arc AB? 50. So now the question that they ask is, well, how big is arc APD? Good, 50 plus 50 plus 50 is what?
150.
150. But that's not what they're asking for, is it? Why?
That's for big size.
It asks for this side, so what's a full circle?
360.
360.
300. Same number.
And I know that this part up here is 150.
210.
That leaves it with 210 degrees. Are we okay? Okay. Now, it's been a while, but we have this word and it's regular. Does anybody know what the word regular means?
Square.
All the sides equal.
Good, absolutely. Put a great big star on your paper right here. Regular means that all sides are congruent. Okay, that's what regular means. So each regular polygon is inscribed in a circle. What does that mean, inscribed in a circle? It's just inside? And the vertex have to be on the edges. So right here, if I'm talking about a hexagon, I have a hexagon on the inside of a circle, but more importantly, all these points right here have to touch. What else do I know about this hexagon? All the sides are equal, right? In other words, all those chords are equal. But the problem is that now they want to know how big is each arc. Why? Good. A full circle is 360, and because they're regular, they're all the same. So 360 divided by 6 is 60 degrees. So that means that each arc is going to be 60 degrees. Does that make sense? Okay. Now let's take a look at the next one. A pentagon. How many sides does a pentagon have?
360 divided by 6.
360 divided by 6. I'm sorry. Pentagon is how many sides?
5.
5. What do you know about your pentagon? It's what? Good. All sides are congruent because it's regular, so all these chords are the same. I know that it's inscribed, so that means that all these vertex touch right on the edge of that circle. So what would I do to find the measure of each arc? Good. 360 divided by 5, which is what? Okay, I'm going to give you a second, and I want you to do 3 through 6. Okay, so if I go all the way around, it's 360, and with these sides being the same, so then if I come back and say 4x plus 2x plus 4x plus 2x, right? What is that, 12 x's? That has to equal 360. And then what? Okay, divide by 12. So how big is x? Is that my answer?
No.
Why not? Because they wanted to know the measure of each arc. Well, this arc right here is 2x. How big was x? So what's 2 times 30? 60. That means the arc over here would also be 60 degrees. And up here, this is 4 times x. So 4 times 30 would give me 120. That means the bottom one down here is also. Take a look at number 8. Any ideas? What are some things that I need to notice so I can solve it? That it's isosceles. Those two sides are the same, right? Okay, so these two sides right here are the same. Those are chords, aren't they? And if the chords are congruent, then aren't their arcs the same? So if this arc over here is 7x, that means that this arc over here would also be 7x. How would I set this one up? Add up all the arcs, right? And not necessarily the sides, so the arcs of the circle. So what would I write?
16x.
Where'd you get 16 from? 7x plus 7x plus 4x is equal to 360. So that'd be 18x is equal to 360. Divide by 18. So x is what? 20. So then this side right here is 4 times 20, which would be what? 80, very good. This side over here would be 7 times 20, which would be, and then over here, 7 times 20 would also be 140. And if I add up those three numbers, what should I get? 360. If I got something different, then I've done something wrong. Dude, number 9 doesn't have any numbers.
But you found it the same.
Okay, these sides are the same. Good.
RU 180.
Aha, what's RU called? Aha, and what does the diameter do? Okay, so how big is this arc right here? 180. So what would I do? Divide by 3. So each arc would be 60 degrees. Are you okay? Okay.
Why would it divide by 3?
Because there are 3 chords that are congruent. See those 3 chords there on the bottom? They're all the same. All right, take a look at the back side. Okay, somebody tell me what's this right here called? Radius, very good. Not radius. And then somebody tell me what this side right here is called. It's a what? Chord, very good. So, in a circle, if a radius these got messed up. Are perpendicular to a chord. What does perpendicular mean? 90 degrees. What's the symbol for perpendicular? Upside down T, very good. To a chord. And I just got rid of that other one. Well, I'm just going to write it. And it bisects the chord and its arc. The chord and the arc. What does bisects mean? And it means that it cuts it into 2 equal parts. So that means right here, the radius cuts the chord into 2 equal parts. Which also means that this arc would also be congruent. These arcs up here would be the same. A minute ago, I was looking at that paper plate, you remember? And I told you those pink lines, in order to make them the same, what do we have to do to them? Measure to where? To the middle. Very good. So in order for these 2 chords to be the same, what we need to know is that they're the same distance, or they are congruent to the center. In other words, these dashed lines right here have to be the same. If those distances from the center are the same, then those chords are the same. All right. Oh, look at those pretty shapes. Aren't those awesome? Somebody tell me, what is this line right here called? Radius. Uh-huh. If I continue this line straight down, what would it be called? Radius. And what would this line right here, CD, be called? Chord. So if I have a radius that crosses a chord, and it forms 90 degrees, what do I know about it? Well, it is perpendicular, but what do I know about it? It cuts it in half, right? So that means that each of these would be the same. So in this problem, it tells me that CD is perpendicular to OE. It tells me that OD is 15. And it tells me that CD is 24. So this chord is 24. So how big is each piece? 12. So each of these pieces are 12. But now it's asking how big is just this part. It's what? Pythagorean theorem, how do I know that? Because now I have a right triangle on the inside. Which one is my C? Why? It's your hypotenuse. Very good. So now to solve this one would be a squared plus b squared equals c squared. So that would be x squared plus 12 squared equals 15 squared. What's 12 squared? 144. What's 15 squared? What would I do next? Okay, we're going to subtract the 144. So x squared is equal to, what is that, 81? Take the square root of both sides. So x is 9. So when you get stuck on these problems, you're looking for about 3 different things. Number 1, you're going to look for a diameter, because diameters equal 180 degrees. You're also going to look for radius, or sometimes you can create your own radius, right? Because any radius in a circle is going to be the same. So that radius right there was 15. This radius right here would also be 15, wouldn't it? If that piece is 9, then how big is this little piece down here? 15 minus 9, which is 6. Are we okay? All right. I'm going to give you just a second. I want you to try 1 through 9. I'm going to give you just a minute or so. I want you to try 1 through 9. First off, it says encircle P, so that tells me that P is the center of my circle. It then tells me that CD is 24. What is CD?
Chord.
A chord. Very good. And it says it's 24. But somebody please tell me what's this line right here. So what happens when we have a chord and a radius? And it is 90 degrees. It what?
Bisect.
Good. That's what we just talked about right here. It bisects and it makes this little piece and the arc congruent. So that means that these two are the same. It also means that these two arcs are the same, doesn't it? So tell me, how big is each of these pieces?
12.
12. So we have 12 and 12. And then they told me right here that arc CY is 45. So that means this arc is 45. Okay? And then right here, what does it tell me? That PQ is equal to PR. What does that matter? Good. It means that those chords are the same. So all the information I have on the right side can be transferred exactly as it is over to this other chord. So I have 12 and 12, 45 and 45. So how big is AQ? How big is AB? How big is arc AX? How big is RC? How big is arc DY? How big is arc XB? How big is segment QB? How big is arc AB? And arc CD? Okay, was that so hard? It looks really difficult though, if you just glance at it, right? Okay, so just narrow it down, and remember, anytime you have a chord and a radius and they hit at 90 degrees, then you can bisect those segments. Okay? I'm going to skip down to the bottom because I want to make sure I hit there, and then I'm going to come back and work this next section for you. Okay, it says right here, a chord of a circle is 20 inches. And then it tells me that my chord is 24 inches from the center of my circle. What happens when we have a chord and a radius? Because they're perpendicular, they bisect each other, right? So wouldn't this be 10 and 10?
Yes.
And now it wants to know, how long is the radius? Do we have a radius? Okay. You can add a radius at any time. Would this be a radius right here?
Yes.
Ah. Why would I put the radius right there?
You can make a triangle.
What kind of triangle?
90 degree triangle.
A right triangle. And when I have a right triangle, what can I do? Pythagorean theorem. 10 squared plus 24 squared equals c squared. I don't know what 24 squared is. 576, thank you. So that makes this 676. And then the square root of 676 is 26. So my radius is 26 units. So when you get stuck, you're looking for diameters, radiuses, chords, and you're going to look, you could possibly write in a radius and you're look for right triangles. Okay, up here. It tells me that DG and GU are the same. Oh look, this one's 3, so that means this one right here is 3, right? Somebody tell me, what is this? The blue line. It's a radius. Somebody tell me, what's this blue line? What do you know about the radius of a circle? Half of the diameter. Aren't that all the radius going to be the same? How big is this radius? So how big is this radius? Oh, but that piece is 3, so how big is this piece? Aha. And remember, they told me that these were the same distance apart, so these rules apply to the other side as well, don't they? So that means this little piece is 2. And if I draw this radius right here, wouldn't that be 5? Okay, we're not going to worry about these, by the way. So how in the world would I find out how big this piece is? Pythagorean theorem, because right here I have a right triangle. So it would be x squared plus 3 squared equals 5 squared. X squared plus 9 equals 25. Subtract 9. So x squared equals 16. Square root 4. Oh, just kidding. It's a 3, 4, 5 triangle. Do you remember 3, 4, 5 triangles?
Yeah.
We didn't even have to do any of that work, did we? So how big is TU? 4. How big is CD? You said CD was what? 4. Very good. How big is TR? How big is G? What does that say? Each? How big is GD? 3. And we're not going to worry about those. Good. Okay. They should